Hi, and welcome to the latest of the Kavli Foundation Spotlight Live webcasts, which offer you a chance to hear from scientists on the cutting edge of discovery. My name is Adam Hedhazy. Today, we're going to talk about NASA's big plans to bring back a chunk of an asteroid to Earth. Asteroids are space rocks left over from when the planets in our solar system formed some 4.6 billion years ago. Earlier this month, a spacecraft called OSIRIS-REx launched and is now cruising toward an asteroid named Bennu. Once there in 2018, OSIRIS-REx will study Bennu in unprecedented detail. The probe will then collect up to a few pounds of material from the asteroid's dusty surface for delivery to Earth in 2023. If successful, this will be the first asteroid sample ever collected by the United States and the biggest sample return since astronauts brought back a bunch of moon rocks almost a half-century ago. So, why are we going to the trouble of visiting Bennu anyway? Joining us today to discuss the promise and challenges of the OSIRIS-REx mission is Richard Binzel. Richard is one of the world's foremost experts on studying asteroids and a co-investigator on OSIRIS-REx. Based at MIT, he's also affiliated with the Kavli Institute for Astrophysics and Space Research. Joining us as well is Beth Ellen Clark. Beth is the mission asteroid scientist for OSIRIS-REx, which means, among her many other duties, she'll be coordinating the teams making the tough calls about where the probe should gather up samples. She's a physics and astronomy professor at Ithaca College. Also with us today is Bashar Rizk. Bashar is one of the people behind a suite of cameras that acts like the eyes for OSIRIS-REx, allowing the probe to see and navigate around Bennu. He's a senior staff scientist at the University of Arizona. Welcome, everybody. Thank you for being here today.
Hi, Adam.
Hey, welcome.
Great to be here.
Pleasure.
All right, guys. Excellent. A quick reminder before we get started. If you have questions for our panel, please send it by email to info@kavlifoundation.org or tweet us using the hashtag KavliLive. We'll get to as many questions on air as we can. I'd like to go ahead and throw out the first question, which is, so there are many thousands of asteroids in our solar system. What is it that makes Bennu so special? Why Bennu? Richard, if I could start with you, please.
Sure. Thanks, Adam. It's a pleasure to be here. Thank you to everyone who's tuned in. Indeed, there are about 10,000 asteroids that we know that don't stay all the time in the main asteroid belt. In fact, they have orbits that come near the Earth. And we, as an astronomer, we try to sample those with spectroscopic instruments. We use telescopes to try to decode what they are and what they're made out of. And out of those few thousand that we've measured some basic compositional information on, there's a subset that are easily accessible. They're in orbits that are very easy to reach from the Earth. And there's a subset of those that look like they have a very primitive kind of composition. And with that, we think we mean they have an organic carbon chemistry that's like the earliest chemistry of our solar system. And when you go through steps, sort of like climbing to the top of a pyramid, you get this one very special object called Bennu that looks like one of the best places that we can go to try to sample the earliest chemistry of our solar system.
Fantastic. I want to go ahead and ask, and we'll dig down on that a little bit further later on. Now, what about OSIRIS-REx? Let's talk a little bit about how this spacecraft is specifically designed to solve some of the key mysteries about Bennu and let us know more about origins of the solar system and of life itself.
You want me to take that, Adam?
Yeah, anybody feel free to jump in on that. Let's, yeah. And actually, Bashar, let me go ahead and mention that indeed you are, as the instrument scientist for the trio of cameras there, which are called OCAMs. Those are going to be the eyes of OSIRIS-REx. So tell us about, maybe that's a good place to start. Tell us about how OSIRIS-REx is going to see its way to Bennu and how it's really specifically designed to answer these interesting questions.
Well, OSIRIS-REx does what we can't do, which is to go out in space ourselves and examine this rather remarkable asteroid that is also remarkably accessible to the Earth. So if we think of OREX as a person, the solar arrays are its arms, the high gain antenna is its mouth that it uses to communicate to the Earth. And on top of its science deck, there's a sample return capsule, and that is the thing that will be used to send the sample back to Earth safely. Behind OSIRIS-REx, almost like a scorpion's tail, is the sample arm that will reach out, kiss the surface of Bennu, and gather the sample. The instruments that populate the top of the deck, including the cameras, are designed to examine this object and make it safe for us to sample. Find the interesting spots on the surface of Bennu that we will feel is worth our time to go and collect. So when you get to Bennu, everything will be working in a concerted fashion to try to gather all the information you'll need to collect a sample safely.
Yeah.
Fantastic.
I'll just add to that, in addition to the cameras, we have 3 fantastic scientific cameras in addition to our navigation cameras. But we also have, for the first time going to an asteroid, a thermal emission spectrometer that's going to measure the thermal physical properties of the surface and tell us 2 different things. It'll tell us about the composition out into the thermal infrared, and it'll tell us about the thermal inertia of the surface. And this is a very interesting property because it turns out it influences the orbit of Bennu over time.
Yes, and we will be getting to that in just a moment as well. Actually, Beth, let me go ahead and ask you a little bit further to dig down on this this concept here. You mentioned it, and some others have mentioned it. Richard just alluded to it, about Bennu being a, quote, time capsule dating back to the birth of the solar system. Could you go ahead and break that down? What does that mean? What might we find by opening this time capsule on Bennu to the origin of the solar system?
Yeah, I'll give that one a try. So we hope that by grabbing a sample from the surface of Bennu, we'll be studying material that was left over from the formation of the solar system, that it's in its most pristine state, and that it has not been heated up or processed in the past 4.5 billion years. We want stuff that is very close to, we think, in composition to what we see in interstellar environments, what we see in circumstellar environments, such as aliphatic hydrocarbons and polycyclic aromatic hydrocarbons, things that are just really, really primitive and pristine. We think we'll find organics on Bennu by analogy with some meteorite samples that look like they could be similar. And we think we'll find areas on Bennu, we're hoping to find areas on Bennu where we'll find hydrated minerals right in proximity to anhydrous minerals. And this is a very exciting possibility that would go along with having very pristine samples. So they will all tell us about the early formation time of the solar system.
Excellent. I'll ask you a follow-up on that in just one moment. Let's pause here for a minute just to remind viewers that they can ask questions by sending an email to info@kavlifoundation.org or tweet us again using the hashtag KavliLive. So, interesting about the different materials that we expect to find in different places on Bennu. So I want to then ask how are we going to decide what places to sample? There could be a lot of things that we would be after, but how are we going to really boil it down to say, okay, this is what we have to get? What factors will drive the decision of what samples we try to get?
Can I go for that one too?
Yeah, go for that one, Beth.
That's for you.
Okay.
Please
All right,
do.
so good. Our main sampling site will have to satisfy 4 criteria. It has to be safe so that we can descend to the surface with the spacecraft without harming it. It has to be accessible such that our flight dynamics team can accurately deliver the spacecraft to the site that we choose. It has to be sampleable such that it has enough gravel-sized material that our sampling mechanism will be able to capture some of that material and stow it successfully. And more than anything, it has to be scientifically valuable, and it has to be a region on Bennu that we feel gets us closest to our origins in terms of those compositions and textures that I spoke about a few minutes ago.
Excellent. That actually segues us nicely into a viewer question. Stephanie Buckland asks, what would scientists expect to find from material on Bennu that would help shed light on the origins of organisms on Earth? I'll put that out to the group again. Beth, that may be most in your wheelhouse to start, but anybody feel free.
Well, one of the questions that we might be interested in is, what is the handedness of the amino acids, any amino acids that we detect in the sample? Is it left-handed like much of the biogenic amino acids on the Earth, or is it something else?
Right. Just to explain that a little further, that so the basic amino acids for life, they all have sort of one orientation, if you will. I believe that we find here on Earth, but there could just as easily be a different orientation. Could you guys explain that a little bit further? Just want to make that point clear.
Go for it, Beth.
Thanks, Bashar. Yeah, I think this is called, did you use the chirality nature? Yeah, so amino acids have two possible orientations in nature and chemistry and physics, and yet in most of Earth and most of biology on Earth, we only find one chirality. So yeah, what happened to the other side, the other side of us? I think the other interesting molecules we'll be looking for are the organics, the hydrocarbons, and what state are they in, and what are their ratios compared to each other, and what does that tell us about Bennu in relation to what we can see about other star-forming regions?
Yeah, I just add that I think it's just the complexity of the hydrocarbons that we see. Do we get all the way to amino acids and so forth? So I think it's really trying to understand how complex is the carbon chemistry of our solar system, or how complex was it at that very early stage.
And don't forget, we're trying to understand the basic origin of the solar system itself. So one of the big questions is, how well mixed is the material of the solar system, the early solar system? Did it separate into zones that didn't have much contact with each other? Or was there a lot of mixing back and forth? That's something that Bennu might be able to answer.
Excellent. Yeah. Fascinating. Another part of this mission, of course, is, and we touched on this a little bit earlier, is to try to nail down the odds that Bennu might someday collide with our planet. I wanted to ask, how real of a possibility is that? And Richard, let me put that your way first, as of course you're the you're the creator of a scale that grades the danger posed by asteroids. So, what do we think about Bennu?
So the scale is something called the Torino scale, which looks at sort of the century, the prospects in the coming century of any kind of impact. It turns out to itself is the chance of impact is so far in the future and so small, thankfully, that it doesn't even really rank on the scale. So that's good news.
Yes.
Yeah, that's right. Eventually, time will get there. But the number is about the number is at one chance in 2,700. And I like to say that's a 2,700 to 1 odds in our favor that at the end of the 22nd century, that when Bennu comes close to the Earth, that it will miss. And so one of the things we're going to find out, or most likely we'll find out, as we measure precisely Bennu's orbit, we'll find out that it is, in fact, not any threat, even in the far distant future. But one of the key things we want to find out is, how does Bennu sort of feel its way around in its orbit in response to how it's being heated by the sun? There's something called the Yarkovsky effect that will heat up the asteroid, and when it re-radiates, when that heat radiates away, it provides a little tiny push on the asteroid. And if you do that over decades and centuries and thousands of years, you can slightly change the orbit. So that's something we want to understand about Bennu itself, so we understand its potential in the long-term future. But I think more importantly, it's not really just about Bennu. It's about trying to understand how all asteroids respond to this kind of subtle pressure, subtle forces in the solar system, so that we can better understand of the many asteroids known that are in the vicinity of the Earth, just what are their prospects, what are their hazards, looking literally centuries into the future.
Gotcha. And then a question that follows from that is, I know a lot of viewers are asking, so what if Bennu did hit Earth? Let's say that turns out the calculations, the odds end up not in our favor eventually. How much damage would Bennu do? And how would it stack up against some of the major asteroid impacts in Earth's history? I understand that the leader of the OSIRIS-REx mission, Dante Loretta, he recently did some back-of-the-envelope calculations on this. So if you guys could share those with me. Richard, this might be a good one for you as well.
Sure, I'll pick it up. So again, that was not a warning. So again, the chances are incredibly small of Bennu posing any threat, even for the long term, but that's something we want to address. But an object of the size of Bennu, about 500 meters across, hitting the Earth would end up making a crater on the Earth's surface. And I think the estimate is about 3 kilometers, is it? No, 3-mile wide crater on the Earth. And that would really be bad news for a congressional district or a few congressional districts were they to land there. So it is certainly quite small compared to the literally catastrophic impact that we think damaged the ecosystem of the Earth 65 million years ago. That was the event, we think, an asteroid impact occurred at the end of the Cretaceous period, 65 million years ago. And the result was 80% of all the species living on the Earth perished over some very short interval of time, including the dinosaurs. So we think the dinosaur demise was due to an asteroid impact. So Bennu, on the grand scheme of things, is not the end of civilization, is not the end of life. It's just a really bad day for a substantial region of a country. So these things do happen over thousands and thousands of years timescales. The good news is in the short term.
Oh, sounds like we had a quick cutout there. Sorry,
No
Richard,
worries.
were you all wrapped up?
Yeah, go for it.
Okay.
Carry on. Unless Beth or Bashar, you want to ask?
Just to add something to what Richard said, that the object that is believed to have wiped out the dinosaurs is probably of the order of 20 times the diameter of what Bennu is, and probably, scaling up in mass about 80,000 times the mass. So it's a different order of object entirely.
Yeah, thank you. Thank you.
Yeah, I'll just add one thing. So with the thermal emission spectrometer experiment in particular, we hope to measure the thermal inertia of Bennu, and by extension, understand how the thermal inertia of these small objects that are in near-Earth orbit over time affects their orbits. So we hope to really pin down the extrapolations that we can make with orbits of these asteroids into the future and narrow down their possible positions in time and space so that we have a better understanding for a lot of small objects like this, not just Bennu.
Very good. I'm going to go ahead and throw in some viewer questions now. And one, this is just a good thing to kind of get out there. James from Cambridge is asking, what is the difference between an asteroid and a meteor and a meteorite? Could you guys let us know? What do we have there?
All right. So this is a great question. An asteroid is an object in space. A meteor, if an object is entering the Earth's atmosphere and is in the process of vaporizing in the atmosphere, we call that a meteor. And most meteors you see, like a recent meteor shower, like the Perseids you see in the summer, are really tiny grains of dust. And the reason they glow is they're moving so fast when they strike the air molecules that they heat up, and the little dust grains actually vaporize and they create light, and you can see it. And finally, you get a meteorite if one of those objects is large enough, sort of the size of a beach ball or a small car. Is large enough, it can break apart, but fragments can survive to reach the Earth's surface. And those samples that we pick up are called meteorites. So a meteorite is a sample, and this is a pretty famous little meteorite sample. It's called Tagish Lake. It's a carbon-rich kind of meteorite. We think Bennu might be something like this, but the difference is that the sample we'll get from Bennu will be pristine. It will never have been contaminated by the Earth, and we're going to see basically as pristine, or what we hope we'll see is pristine or as old and organic rich as any object we've ever sampled before.
Fantastic. All right, that one was knocked out of the park. Thank you for bringing in the prop there as well. Excellent. Another viewer question on Twitter. Linda Marceau asks, how many kilometers will OSIRIS-REx travel to Bennu and back? I'm going to send this one over to Bashar, and if you can give the answer in miles too, and also just give us a feel for what OSIRIS-REx's overall journey will look like.
I believe the number is close to 6 billion kilometers, 4 billion miles. That OSIRIS is in an orbit that takes it around the sun. Did I say OSIRIS? I meant Bennu is in an orbit that takes it around the sun 5 times every time the Earth goes around the sun 6 times. So it's in a 6 to 5 resonance with the Earth's orbit, which is unusual and makes it practically a next door neighbor or even a satellite of the Earth, because clearly the body in the solar system that is most influential over the fate of Bennu is the Earth. So to go to Bennu, the best thing to do is to launch your spacecraft, launch your rocket at this time when Bennu and the Earth share approximately the same region of space. Every 6 years they come to this spot. We didn't do that. We launched a year early just to give ourselves an extra year in case something untoward happened while we were constructing our spacecraft. So when we meet here again, if we do, in September 2017, a year from now, Bennu and the Earth will be at that special location. And at that point, OSIRIS is going to dive under the surface of the Earth and then get a little tilt upward into Bennu's orbit, and then join Bennu after about a year in space. At that point, it'll have about 2.5 years at Bennu to do a lot of investigation and hopefully gather a good sample, and then about 2 to 2.5 years to get back. So it's by the time it comes back in 2023, it will have gone around the sun 7 times by my count. 6 or 7 times. Okay.
Racking up the miles on the odometer.
Racking up the miles.
Indeed. Excellent. Let's talk a little bit more about the sample collection itself. So now, OSIRIS-REx is going to use a new method for collecting material.
How you doing, man?
The spacecraft will get to within 2 or 3 meters of Bennu, I understand. Then it's going to extend a robotic arm that has a sort of a suction cup-like device almost at the end of it. And what will happen is then that device will spray a blast of a nitrogen gas to knock material off of Bennu and into the collection cup. So it sounds kind of complicated. Why not just try to land on Bennu and scoop up a sample?
It's not so easy. I mean, I should think that anyone watching the fate of Philae, that marvelous lander that was on the Rosetta mission, would get an idea of how complicated it is to operate and touch and stay on a body with as little gravity as Bennu. So I think some years ago, we were part of a study that tried to look at all the different ways you might want to gather material off an object like Bennu. We examined something like 20 to 25 different ways, and I think most everyone at the end of the study who had participated was convinced that we had the best way.
Excellent. And then a question about asteroid mining. A number of companies are looking into sending spacecraft to asteroids at some point in the future here to extract precious metals and materials. I'm wondering how OSIRIS-REx will help pave the way for this sort of activity in the final frontier, and perhaps with this new sample collection technique, how that might tie in.
You gonna try that, Beth?
Yeah, sure. So I think one of the things we're going to learn a lot about is how to manipulate in very low gravity environments, and what we can get away with, and how to work with the time delay, and learn about the gravitational field of the asteroid, as well as the forces that we feel as we descend to the surface and touch down. So I think we're going to learn a lot about operations in these very low gravity environments, and that'll be helpful for such scenarios for the future.
I just follow up in terms of what Bennu is made out of. One of the things that when you send humans into space, they get thirsty. And we think asteroids like Bennu, if water is available in any of these objects, this is the kind of object that might have a fraction of a % of its total mass in water molecules that somehow you might extract. So it's a good test. That'll be one of the things we'll want to understand when we get the sample back is, does it show any potential for being a source of water in space.
Could I ask you guys a question? Do you think that there's water there 1 meter beneath the surface? As I heard suggested in a talk recently by John Lewis that, objects like Bennu, even though they've been around the sun, would have been protected and store a reservoir of water beneath the surface. No?
I don't think so. Not very likely anyway, given the current models and disruption models for these asteroids and how they're impacted over time in the near Earth space, etc.
We wish it were true, but the likelihood is not.
Bummer. Yeah, that would have been nice. Question then about the history of sample returns. Now, Bennu will not be the first space rock material we're bringing back to Earth, but let's go ahead and talk about what's been done previously and how Bennu will move the ball forward and give us a lot more to work with than we've had previously.
Beth, why don't you talk about Hayabusa?
Yeah, well, as we mentioned, it's very difficult to maneuver a spacecraft around these low gravity bodies. And on the Japanese exploration mission in 2005, we learned that up close and made several difficult maneuvers that didn't go as planned. And unfortunately, the sample acquisition mechanism was only able to trap a few grains in the sample return mechanism. So we only have a few grains from a small asteroid that have been returned to Earth by human beings. That was the Japanese and some American collaborators on that mission. We have a few missions that have come back with samples from the tail of a comet and with samples from solar wind. And apart from the Apollo rocks that the astronauts reached down and grabbed up and brought back in the spacecraft from the moon, I think that's pretty much it for the United States so far. Does anybody want to correct me?
No.
Yeah. So getting up to 2 kilograms of rock and gravel and soil and the very optical surface of an asteroid in a controlled and well manipulated spacecraft down to the surface and back into the sample return capsule will be a new event for us in asteroid operations.
Yeah, Beth, I'll maybe just add one more thing is we're getting a sample and we know its environment from which it comes. In other words, we will have a context for this sample. We will have been studying the asteroid for more than a year to try to pick out where we're going to get that sample from. And we'll know how representative that spot is relative to everywhere else on the asteroid. So it's not only that sample, but it's the context. We'll know everything about it. These meteorites are fantastic, but they don't come with return address labels. That's their problem. So we love them in our laboratory. They're one of the best things that happens in science is to get these samples. But without that return address label and the context, it's really hard to piece together this early history of the solar system that has us all so fascinated.
Yeah, I was going to say, where'd you get that sample at Tagish Lake, Rick? That must have really...
Yeah, it's the MIT meteorite collection. Oh, that's where that is.
I'd love to have a piece of that.
Excellent, guys. I think we have time to squeeze in 1 or 2 more questions. One thing I want to ask about, are there any other nearby asteroids that we might visit soon? Are there some other missions, sort of like OSIRIS-REx, in the works? And what kind of info might we glean from a visit to an asteroid, perhaps unlike Bennu?
Boy.
How about you, Rick?
I wasn't worried about that. There are, in fact, a lot of asteroids that are in relatively accessible orbits to the Earth. But one of the fascinating things, in a sense, it's a problem, and it's a thing that bugs me, is we really know of only a fraction of all these asteroids that are in the vicinity of the Earth. Our survey capabilities are still in their early stages. And if we had more extensive surveys to penetrate and discover objects down to smaller and smaller sizes, we'd find that things about the size of a UV come wandering through inside the orbit of the moon every week. So there are a lot of these objects out there that have great potential for exploration. great potential for space resources, but we simply don't know about them. We don't have the capability to find them many years in advance and then plan a mission to them. Many of them you see in the news pop up from time to time, that we happen to find one a couple days before it comes wandering by. That's just the beginning of our capability, and I'd like to see us really catalog these millions of objects that come very close, and really make a catalog of the most accessible objects that future miners or future astronauts can go and interact with.
And some of these are destined to fall into the sun. We see some of those falling into the sun and doing interesting things as they get swallowed up. Others still are out there in orbit.
Excellent. Sounds like we have a lot more potential future targets for these sorts of missions.
Absolutely.
Right. Fantastic. All right, guys. So I think this is a good time to wrap up. I want to thank everybody for being here today. Richard, Beth, and Bashar. Best of luck, guys, with this exciting mission to Bennu.
Thanks, Adam.
Thank you.
Thanks. Pleasure
Been a pleasure.
Excellent, guys. This Hangout will be hosted on the Kavli Foundation's website and on its YouTube page. To find out about upcoming Kavli Live Hangouts, please follow the Kavli Foundation on Facebook and Twitter. All right, everybody, have a great day, and thanks for tuning in.
See ya.
Thanks.